All right. So, hello, everyone. I'm glad to open this term's reading group series. I will just briefly introduce myself. My name is Alberto Bernacchia. I'm a former member of CBL. And since a couple of years, I moved to MediaTek Research, a company based in Cambridge. Jezabel also works in the same company, and I'm presenting with me today. So we are in the semiconductor and microchip industry, but we also do fundamental research in machine learning. So we are very interested in this reading group series, and we are happy to contribute. Today we talk about implicit regularization in deep learning. So we picked this topic because we think it's quite useful for understanding optimization in big neural networks. And this is something often non-trivial to do in practice. And we also think that this in general is an interesting field that can bring new theoretical ideas and discoveries. All right, so we start from the observation that big neural networks trained by gradient descent generalize well, even without any explicit regularization. So this is surprising because when you have a lot of parameters, then your model is supposed to overfit and generalize poorly, but somehow that doesn't happen. And we review three separate non-exclusive theories that have been developed in the past few years to explain this observation. And the basic idea is that the optimizer, in particular gradient descent, tends to avoid the bad minima of the training loss and finds only the good solutions that generalize well. So in this sense, the choice of the optimizer implicitly regularized training, and in some cases, in particular for 2 and 3, it's possible to derive mathematical expressions for the regularizer. So we are not talking about pack-base, which is also represents a very nice account of this observation, because we had a very good reading group about this in the last term. So I suggest that you look back at those slides if you're interested. And I saw this morning that there's actually a talk about pack-base this afternoon as well by Andrew. So that's nice. All right, so we start from an observation made 4 years ago by this famous paper that now has more than 3,000 citations. So in this paper, they make up a data set where they randomly shuffle labels across images. So each image is associated with a random label that is the wrong one in most cases. And then they train a variety of neural networks on this data set, including convolutional networks such as Inception, AlexNet, and also some multi-layer perceptrons. And so these networks, I mean, they are big enough to get 0 training error on the random labels. So this is shown by 100% accuracy when fitting random labels. And so they have enough capacity to memorize the training data. But obviously, they have chance performance on test data. So here is about 10% because CIFAR has 10 classes. So these models have about 1 million parameters. So they're not really big. I mean, in the sense that nowadays, truly large models have billions of parameters. But the point here is that they are big enough to memorize this relatively small data set. I think CIFAR has about 50,000 images. So the main result here is that when they trained, so basically they retrained from scratch, the same neural networks now on true labels, surprisingly, they find that they generalize pretty well. So they still can find the 100% training accuracy, but then the test accuracy is pretty good. And interestingly, this is true regardless of whether regularization is used. Here they use, they may or may not use weight decay and data augmentation. But the improvement in the test accuracy, even when they use explicit regularization, is not huge, right? So, so the bottom line is that neural networks that are big enough to memorize random labels are still able to generalize when trained on true labels, right? And so why is this surprising? So, for example, we could look at some predictions of learning theory, in particular, if you look into the definition of mathematical complexity, that is basically defined precisely as the capacity of a model to fit random labels, right? So here, random labels are the sigmas, and they are just binary labels, plus minus 1. M is the number of data points, of training data points, and this supremum finds the model F that has the highest correlation with the random labels within some model class. And so when F has also binary outputs and is able to perfectly fit random labels, then the complexity is equal to 1. And so without going into the details, many of you probably know this already, we can use this bound. Well, we can use this number to bound the test error by the training error, and then the complexity. In this case, complexity is basically 1. I mean 100%, and so this bound is useless in practice, right? So we cannot use this to really explain why this neural network generalized decently, pretty well. And so the hypothesis is that, well, so we need to note that the bound holds for every model in the model class, but it might be that we never get to see the worst cases, right? We never get to see the bad models. Somehow we are able to find only the good models that generalize well. So the hypothesis is that the optimization process, in particular gradient descent, is able to find the good models. So in other words, even if there are some bad models that generalize poorly, SGD will not find them. Okay, so why does SGD find good models? The first idea to answer this question is about flat versus sharp minima. The hypothesis is that for the same value of the loss function, of the training loss function, sharp minima generalize poorly, while flat minima generalize well. And the idea is that the stochastic gradient descent is going to avoid sharp minima. So this figure provides some intuition on why that may be the case. So here the test loss is shown in the dashed red line, and is assumed to be a perturbed version of the training loss, which is shown by the full black line. So if the model ends up in a sharp minimum, so basically here, then the test loss will be pretty bad. While if it ends up in a flat minimum, then the test loss is still okay, still good. I mean, this is obviously just a toy illustration. So in the next slides, I'll try to convince ourselves more formally the flat minima are indeed better, in particular from a Bayesian point of view. Please ask questions if you wish. All right, so here I'm showing the expression of the posterior over some parameters W, given training data XY and model M. And this is proportional to the likelihood times the prior, as usual by Bayes rule. And so we assume, I mean, this is as usual standard, we assume that the data points are independent. And we express the likelihood in terms of the entropy of the predictive distribution that is estimated by a sum over on the training data. This entropy is typically used as the loss function in many machine learning problems. And we also assume a simple Gaussian prior on the parameters W with some scale parameter lambda. Then the log posterior takes the form of a regularized cost function. This is equal to just the entropy plus basically a weight decay regularization term that comes from the prior. And so if we do a maximum a posteriori estimation, then we are looking to minimize this cost and find some optimal parameters. All right, so now this is all obvious if you want. So now we would like to compare two models, M1 and M2, to figure out which one of the two models is better, in particular, which has sort of a higher posterior. And so the ratio of the posterior is equal to the evidence ratio times the prior ratio. And when we assume that the prior over the two models is the same, then the ratio is equal to 1. So we focus on the evidence ratio to find out which model is better. And so if you compute this evidence, so this is given again by the product of the likelihood and the prior marginalized over the parameters. And so again, we have the exponential of the cost function. And if we assume that the cost function has a strong peak around its minimum, well, around a minimum, then we can use Laplace approximation, which basically Taylor expands the cost function to second order around its minimum. And so therefore, we find that under this approximation, we find that models with higher curvature have lower evidence. And here the curvature is defined by the eigenvalues of the Hessian of the cost function. So the lambda i's here are the eigenvalues of the Hessian of the cost, because we have expanded this cost to second order. So we get the Hessian of the cost, and those are the eigenvalues of the Hessian. So if you look at the eigenvalues of the Hessian at the minimum, at the W0, these are basically give us the curvature of this minimum. And so for the same, so if we want to compare two different models which have this, let's say they have the same value of the cost function, then basically the models that have flatter minima, so with the smaller curvature, they have higher evidence, and so they are expected to work better.
Sorry, can I ask what is lambda in the above equation?
So lambda is the scale of the prior, and lambda i's are the eigenvalues of the Hessian of the cost, so the curvature. So the curvature, I mean, okay, so this is a little bit sloppy in the sense that there's no one number that identifies the curvature. This is the entire spectrum of the Hessian that is so basically different eigenvalues of the Hessian. They give the curvature along different dimensions.
Mm-hmm. No, I understand lambda I, but what is lambda? The scale of the prior?
Yeah, so lambda is the scale of the prior. I basically define the prior of the parameters, and this is just
I missed it. Thanks.
Mm-hmm. Hi, sorry, can I ask a question?
Sure.
So I've got a couple questions. One of them is, this is supposed to be explaining why neural nets generalize in practice, but it's like a Bayesian approach, and usually we don't train Bayesian neural networks in practice. So this seems a bit like a different model. And the second question is, this has to do with different models corresponding to different minima of the loss, but it's perhaps more natural to think of there just being one model that covers all the minima. So like, how does that get explained in the paper?
Yeah. So good question. So the first question I basically want to answer in the next slides, because I'm going to show that when you do a stochastic gradient descent under some approximations, you're basically sampling from the posterior. And so in practice, you will sample more with a higher probability. You will sample modes that have that are more narrow, that are more wide. So in this sense, basically stochastic gradient descent avoids the sharper minima. And I mean, this doesn't prove that they generalize better. It only indicates that yes, so they have a higher evidence. I don't know if this will answer this question. Maybe you can go through the slides and then you can ask the question again.
Cool, thanks very much.
And for the second question, yeah, so this is also, I had the same question when reading this paper. I couldn't really find the final answer to this, but yeah, I agree. So basically, these two models are supposed to identify two different minima of the cost, and there is some discussion about this in the appendix of the paper. Yeah, but yeah, basically, I think your intuition is correct.
Cool. Yeah, I think there's like some classical discussions about like thinking about the evidence of different modes that goes back to like the early 2000s or even the late 90s. If I can find that, I might send it if that's useful. Thanks.
Yeah. Yeah, I think these works are also cited in this paper. It's just that this paper puts it into the context of generalization in big neural networks, and also presents some experiments that I will show then in the next slides. Obviously, this kind of math has been known for before 2018. I agree with that. All right, so this is an example of basically test of the idea that when you have high, basically lower curvature, you have higher test accuracy. So this is a test on some convolutional networks, LANet and ResNet, on different data set, MNIST, Street View, and CIFAR. And indeed, they find that test accuracy is higher for lower curvature. So this is the sum over the log of the eigenvalues of the Hessian. Well, I think a subset of them. And so yeah, so next, so this is okay. So this was about.
Yeah. Can you hear me? I have a question about that last bit.
Yeah.
Yeah. Where are they getting the models here? So I mean, some of these models have really bad test accuracy. So I don't imagine that they've actually been like trained or not trained much.
Mm-hmm. Yeah, so I think yeah, the purpose of this work was not to get very high accuracy. It was mostly to test prediction of the theory.
Oh yeah, sure, but I mean, there's kind of two things that are going on here, right? So I mean, you might say that there's something besides just the sharpness of the minima that the gradient descent is doing, right? So I mean, I guess I'm just wondering, like, are these sort of randomly initialized or like partially trained?
Yeah, so good question. I think they are randomly initialized, but I'm not sure about the details. I would have to look back at the paper.
Okay. Yeah,
I think they are randomly initialized. Yeah. All right. So okay. So the next step is to prove that stochastic gradient descent tends to find flatter minima. So in the next slides, I will show that we expect this to be the case. And so here I'm showing the update of stochastic gradient descent. So delta W is the update. It's just the difference between the new value and the old value, which is equal to the minus the gradient of the cost with respect to the parameters multiplied by the learning rate epsilon and scaled by n, which is the total number of training data points. So here C hat is not precisely the cost function because it is computed on a mini batch of training data points as opposed to the entire training data set. And so the mini batch is a random subset of B data points that are drawn at random from the total n total training data points. And so here I'm rewriting the update after just adding and subtracting now the full batch gradient. So C is the full batch cost now calculated on the full data set of endpoints. And so the point here is that the full batch gradient is identified as the function that we are looking to minimize. And while the difference between the mini batch and the full batch is interpreted as noise. So the main argument here is that this noise is actually very important. Even if in practice, I mean, when we do maximum a posteriori estimation, we're looking to minimize the full batch cost. This noise allows us, is basically what's going to allow us to avoid the bad minima. And in particular, this noise should be neither too small or nor too large. So if it's too large, then the learning is impossible. But if it's too small, then we may get stuck in bad minima. And so more formally, if we take the limit of infinite training set size and infinite mini batch size, with the mini batch that is much smaller than the training set, then the gradient descent update becomes equivalent to a gradient flow that is described by a stochastic differential equation with Gaussian noise. And so this is a Langevin type of equation, and the stationary probability distribution for the parameters W can be found to be exactly equal to the posterior, where the cost function is rescaled by a temperature T. And this temperature is given by the noise scale. And so if we do the math, then it turns out that the noise scale is proportional to the learning rate times the number of training data points divided by the batch size. And so, I mean, ideally, this temperature should be equal to 1 if you wanted to sample from the true posterior. But the prediction here is that there should be an optimal value of the noise scale that is, again, neither too large nor too small. And so, yeah, so at the optimal value of the noise scale, the model escapes from the sharp minima because those correspond to relatively narrow modes of the posterior. And so this has been tested with a bunch of experiments. And again, you're going to find not state-of-the-art performance here. So again, this is small models on small data. So in this case, is a multilayer perceptron on actually a subset of MNIST because it's just 1,000 training data points. And so what is plotted here is the test set accuracy during training. So it's a function of the gradient descent updates. And so basically the result is that, well, for a very small batch size, then basically no training happens. But then when you increase the batch size, it's there's going to be an optimal value of the batch size. So this is shown here. This is the test set accuracy. I mean, the best accuracy. And there is an optimal value of the batch size, which agrees with the prediction that there should be an optimal value of the noise scale, basically. And so interestingly, you can change the learning rate over a large range and look at how the optimal batch size changes when changing the learning rate. And as you expect from the expression of the noise scale, the optimal batch size scales linearly with the learning rate. So again, under the hypothesis that there is an optimal value of the noise scale, then this is exactly what you would expect. Finally, they also look at changing the number of training data points. Here, the maximum as a function of the batch size is much less evident. But basically, they find that also the optimal batch size scales kind of linearly with the training set size, which is also a prediction of this theory. This is sort of less compelling, but yeah. Other papers show that increasing, so this plot shows the spectrum of the Hessian at the minimum. And so on some convolutional network trained on CIFAR or MNIST, and they look at the spectrum of the Hessian for varying the batch size. And again, they find that when, so when the batch size is larger, then the spectrum has larger eigenvalues, which mean sharper curvature, right? Which was what we expect. And finally, when you change the learning rate, similarly, when you now decrease the learning rate, you also find sharper curvature of the Hessian. So this is other experiment done on fully connected network or convolutional network. So this seems to be also quite consistent.
Just a comment on this line of research.
Yeah.
Recently, there are a couple of papers showing if we use layer-wise adaptive learning rate, we can use a very large batch size. That provide a counter evidence on this research.
Mm-hmm. Interesting. So you say that if you change learning rate only in some layers?
Yes,
then...
there's a formula for deriving layer-wise learning rates, basically using different learning rates for different layers according to the norm of the width in that layer.
Yeah.
Then you can increase the learning rate to increase the batch size to very large numbers.
Mm-hmm.
And the performance of generalization still remains the same.
Yeah, but this is actually similar to what this theory predicts, right? So if you increase learning rate and batch size at the same time, then the noise scale remains the same. So you expect it to have the similar performance. Is that what you're saying?
No. So when we use a very large batch size, the noise in the gradient diminish.
So when you,
yeah, basically it's saying the noise in the gradient doesn't really help generalization.
Okay, yeah, it would be nice if you can send around this work. I'm not aware of this. Thanks.
Sure.
Hi, can I also ask a question?
Yeah.
I have two questions actually. One is the models in the plot where you showed the training or the test accuracy going up and then down. Are they trained to convergence or for a fixed number of steps?
You mean these ones?
Yeah, exactly that one.
Yeah, so here I guess you can see that they're trained to convergence.
Ah, yeah, okay, gotcha. And in the slide before where you show the optimal noise scale, how is that like what is that optimal with respect to? Is like the noise scale that actually recovers the posterior with temperature 1, or is it optimal?
No, so we don't know how to get the posterior with temperature equal to 1 because we only know that the temperature is proportional to this factor, but we don't know the exact value. So therefore, the prediction is that there's going to be an optimal value of this bit, but which we don't know what is this value.
Gotcha.
Yeah.
Yeah. So where does that formula come from? The epsilon n over v?
Yeah. So basically, it comes from doing the math and taking this limit. So I haven't included this in the slides because there's not really time to do that. But you can. So we provide all the references at the end of the presentation, so you can look at the appendix with all the details.
Gotcha. Thanks.
Yeah. All right, so now we move to topic number 2, and so this is about the observation that gradient descent finds minimum norm solutions. So I would like to stress that the results of this section are entirely independent on the results of previous section, and so here we don't look into the effect on noise at all. And results are valid even in the case when there is no noise at all. So when the noise is equal to 0. So this is a completely different line of research. Yeah. And so the bottom line here is that even when you have no noise, gradient descent tends to find minima that have some specific and interesting properties. And so this will be the topic of this section. And so we start from a very simple problem that we understand well. So this is overparameterized linear regression. And then later we move to a more interesting nonlinear problem. So here we are looking to find a minimum of the square difference between target values y and the prediction given by the scalar product of the vector of parameters w and the vector of inputs x. So n here is the number of data points, and d is the number of parameters, and here d is also equal to the input dimension. So this is classic simple linear regression. So if the number of parameters is larger than the number of data points, the problem is overparameterized. And we can find parameters W for which our prediction is exactly equal to the target for all training data points. So basically the training loss will be 0, right? And there is an infinite set. Well, when D is larger than N, there is an infinite set of these solutions W. And so the question is what kind of solution gradient descent finds. So if we do the math, we find that gradient descent finds a unique solution. That is the solution with the minimum L2 norm, provided that we start from initial condition equal to 0. So this can be verified quite easily. I mean, even so, if we run gradient descent here, the batch size does not matter, even with batch size equal to 1. Basically, we know, I mean, this error. So if this is just the error, is just the difference between the target and the prediction. This is a scalar. So the parameters will be just a linear combination of the data points, and with some coefficient. And then if we just substitute this into the, if you assume that we find a 0 training error solution, then we found a unique solution that is exactly the solution of minimum L2 norm. So even if this problem has infinite possible solution, gradient descent is find a very specific one that in some circumstances generalize well, right? So there are many other solutions that are gonna perform very poorly, especially the ones that have very, very big, typically, I mean, at least in many circumstances, that have big value of the norm of W. And so this is, perhaps all of you know this, and I will not go into the details, but similar results hold also for kernel regression, where minimum RKHS norm is found. This includes the case of neural tangent kernel that has been quite popular in recent years. But so the authors of this paper now ask a more difficult question, which is whether gradient descent also find minimum norm solution in nonlinear models. And so this is the topic of the next couple of slides. And so this is a hard question. So they will come up with also a sort of toy problem, but to answer this, but it's nonlinear. So again, we are looking into a loss that is equal to the square difference between a target value, scalar target value, and the predictor f. And they consider, so this obviously this predictor depends on the parameters w and the input data x, where n is the number of training data points. And so they consider the simple case of gradient flow, where w dot is the time derivative of w, which is just equal to minus the gradient of the loss. And then they use an initial condition, which depends on this parameter, hyperparameter alpha, which is quite important. So this parameter alpha is the scale of initialization and will turn out to be quite important. And so they look into this problem, which they call reparameterized linear regression. I mean, effectively, they have a linear regression problem in which the input is just multiplied by a vector of coefficient, beta. But this beta coefficient, they depend non-linearly on the parameters w. So these parameters w are raised to a power of d, and within this sort of toy model, this number d represents the number of layers, the number of effective linear layers. I mean, in practice, this problem is still linear regression. So in a sense, it's trivial. But they find results that are kind of interesting, and we'll see that they turn out to be perhaps useful to understand more interesting applications, as we will see later. And so, so the result is that gradient descent, in this case, also finds minimum norm solutions. So I will not go into the details, it's a little bit complicated, but basically the norm, so beta again is the coefficient of the linear regression coefficient. And I mean, in practice, it's the parameter, except that it's reparameterized by this formula. And so the result is that if the scale of initialization is small, then gradient descent finds the minimum L1 norm, while if the scale of initialization is large, then gradient descent finds the minimum L2 norm. So this is, this is results in qualitatively different solutions, right? I mean, in particular, minimum L1 norm implies sparse solution that in some circumstances they may generalize better. And so this is interesting because it shows that also in some nonlinear model, gradient descent tend to minimize some norm, and but the specific norm depends on for example, in this case on the scale of initialization, and it might depend on other hyperparameters as well. And so yeah, so in the next slides we see a practical example where this finding may be relevant. So it's kind of similar to this, but more interesting. It's about basically low rank matrix recovery using matrix factorization, and so we will see that empirically in that case also it seems that gradient descent finds minimum norm solutions where in that case it's going to be the nuclear norm, but yeah, so I'm gonna talk about it because then Jezabel will take over and tell you about that.
Can I ask a quick question about
that? Yeah.
So I don't really get what's going on at the below reparameterized linear regression. You take the model to be an inner product between two, and then you multiply with the difference between these two sets of parameters. Could you repeat again what's going on there?
So yeah, so if you take the product between the vector x and this beta coefficient, which is w to the raised to the power of d. So there are, for technical reason, there is w plus and w minus. I mean, I can explain this if you want, but the most important thing is that this beta coefficient is not linear in w. So when you compute this gradient with respect to the loss, you're not going to find the same trajectory for the w's as you will find when this beta is just equal to w, right?
Yeah.
You see what I mean?
Yeah, that makes sense.
So the trajectory of the optimization is going to be different just because you have reparameterized. I mean, gradient descent, gradient flow is not invariant for reparameterization, right? So depending on the parameterization that you have, you're going to get different trajectories and also different solutions. So in this case, yeah.
So it's the basic idea. We don't need to understand exactly what's going on there, but it's like a nonlinear reparameterization. It's like some nonlinear model, and then this theorem holds, or is it important for the theorem?
I mean, so in practice, this is linear regression in the sense that you're not solving any problem that is more complicated than linear regression, but because of the reparameterization, you find a different solution. Gradient descent find a different solution, and that has different properties. And the result of this paper is that I think that the main result really is that you can find minimum L1 norm solution as opposed to minimum L2 norm solution. And in this case, this is very useful, especially when you're looking for sparse solution. And when this generalize to a less sort of toy problem, as we will see next, then this might be interesting. And in fact, this is being used also in some applications, this idea. Does it make sense?
Yeah, I think so. Thanks.
All right. Any other questions before we switch?
Yeah, I was just wondering if you can give us any intuition of what's going on in this result. Like, why is it the case that the scale of the initialization has this effect? Like, is it just as alpha goes to 0, like you're getting closer to, I don't know, to initializing at 0, and if you actually initialized some of the weights at 0, then it would be more plausible to stay there. But
yeah, so I don't have very good intuition into this. Maybe when you see the next slides by Jezabel, she will show an example, and she will show that
cool.
that when you have deep matrix factorization, basically you have singular values that start from very close to 0, and then these singular values basically they ramp up one at a time, and which implies that a lot of singular values stay at 0. So that's why you get sparse solutions, because a lot of the parameters actually they just remain at 0, and only some of them jump up and basically get to non-zero values. I don't know. I don't really have a good intuition, but this is the best I can explain.
Thanks.
Yeah. Right, then maybe we can switch now. Okay, so then I'm gonna stop sharing, and Jezabel will...
Can you hear me?
Yeah.
Okay. Let me share. So can you see my presentation?
Yep.
Okay, thank you. So we are going to continue talking about how gradient descent finds minimum norm solutions, and for this, we are going to go back to one of the first papers talking about this, that is called Implicit Regularization in Deep Matrix Factorization. This paper studies the implicit regularization of gradient descent over deep linear neural networks or matrix complexion. What is matrix complexion? So basically, this is a problem where we are giving a subset of entries of a matrix, and we want to obtain all the values of the matrix. This may look like a very simple, easy problem, and it actually is, but it's also still very used in recommendation systems to do collaborative filtering. So what we want to discover is the similarities on the user past behavior and make prediction for this user based on past behavior and other users. So in the example that we have here, we have some machine learning students that basically have read some machine learning books, and we want and have read them, and we want to know which book they should study after. So this matrix completion can be explained as a prediction problem. So how? Basically, we give as an input the row and the column of the matrix, and the value of the matrix, it will be, in this point, will be our label. Or observed entries will be our training data, and or unobserved entries will be our test data. And therefore, our matrix will be basically our predictor. So to solve this prediction problem, we can use matrix factorization. Applying matrix factorization means that we express our matrix as a product of matrices in a way that these matrices have to be big enough so don't constrain the rank of the final solution. And then we apply gradient descent over the resulting loss. So in location yj, I measure the square difference between the given label and my model, that is the product of these matrices. Can you see my pointer? Well, I hope so.
Yeah.
Yeah.
Okay. So as we can see, this expression of the loss don't include any explicit regularization, but empirical results by the first matrix factorization paper shows that if the ground true matrix, the original matrix that we want to recover, have low rank, and we initialize close to 0, and we run gradient descent, matrix factorization will give us good recovery of the initial matrix. So this observation combined with a classic result, much older, just for matrices, that says basically if the matrix that we want to recover have low rank, and we have enough observations, and from all the matrices that fit these observations, we take the one with we will properly recover our original matrix. So the previous observational result and this classic result make that in the implicit regularization of matrix factorization paper, Gunnar-Sekar arrived to the conjecture that for matrix factorization of depth 2, with a small initialization and a small step size, will fit the observation with implicit minimizing the nuclear norm. So basically what it's saying is that the implicit regularization in matrix factorization is the same that basically minimizing the nuclear norm. So there are many ways of defining the norm of a matrix. That is basically the norm is a number which measure the magnitude of the matrix itself, and in this case they are talking about the nuclear norm, that is the sum of all the singular values of the matrix. So in a more recent paper that is called Implicit Regularization of Deep Matrix Factorization, Aurora et al. Tried to run some experiments to check if this conjecture is true. So what they do is, for different matrix completion tasks, they vary the number of observed entries, and they compare the nuclear minimum norm solution to the result obtained by running gradient descent on matrix factorization on different depths. So these are the results. In here we have reconstruction error. Each point in this graph is a different experiment where you have a different matrix with a different number of observations. In this, you have the nuclear norm for the matrix that you are going to recover. And here you have the effective rank. The effective rank is not the real rank of the matrix. The real rank will only measure the real number of zeros that you have in your matrix. The effective rank is a way of measuring the size of your matrix when you have many values close to 0, and they doing for all this for original matrix of rank 5. So what they do is running different matrix factorization problems in gradient descent with different initialization for depth 2, and they also run depth 3, depth 4, and depth 5, but they say that for depth bigger than 3, the initialization doesn't change the value, and that all these curves for bigger depth basically overlap for this problem. So they only plot depth 3. So what we can see is that in the right side of the plot, when the number of observation is high, the matrix factorization will arrive to the same solution, that minimizing the nuclear norm, and they will overlap. The value of the nuclear norm that they obtain is the proper one, and the same for all the methods. And the value of the effective rank is the rank of the matrix, that is 5. But when you have a lower value of observations, when you don't have so many observations, so you are much overparameterized, what is happening is like the nuclear minimization really have a higher reconstruction error. So it's all of this is trained to convergence. So they don't manage to recover the original matrix, and the matrix factorization with gradient descent will not follow the same curve that the nuclear norm. They will have lower reconstruction errors, and they will have higher value of the nuclear norm. Instead, what is happening is that they are going to try to minimize the rank. So the effective rank of these final matrices will be much lower than the effective rank that nuclear norm will give you, and much closer to the ground truth solution. So it looks like, for what they are saying, the nuclear norm may not be able to capture the full regularization. So you need to use a different measure of regularization, that in this case will be the rank. So after this, I tried to understand why this is happening. And for this, they ran some dynamical analysis of the training. So basically, this is trying to characterize trajectories of gradient float. That is basically gradient descent with infinitesimal small learning rate on the matrix factorization. So we define our ground truth matrix or our final matrix as the product of all the different matrices, and each singular value of this final matrix is sigma. So they prove, and I'm not going to show the proof, that basically the rate of change of the singular value is proportional to the square of the singular value to the power of 1 to 1 minus 1 divided by n. So the deeper the matrix factorization, the bigger that the dependence on n we have, the dependence on the depth is. So this will mean that larger singular values move faster, and small ones, so if your original singular value was small in your final matrix, will move slower. So in the case of depth 2, we basically here have 0, so you have basically the square. So you will not see these kind of steps in the single values, but for depth bigger than depth 1, depth 2, and depth 3, we have under reconstruction error that we get by matrix factorization and gradient descent is bigger. When you have deeper matrix factorization, you have a smaller reconstruction error, and you start to see that when you initialize close to 0, the singular values almost do not move. And then in order to fit the observation, they slowly move. They start to move. Then a singular value, in this case is 1, kind of pass a threshold and start to grow according to this equation. If this singular value is enough to fit of observation, the learning will stop. If not, a second singular value will pass this threshold and kind of grow with its power, and so on until you have fit all observation. So the bigger that is, the deeper that is your matrix factorization, the more jumps, more abrupt that are this jump, and more difference there will be between your singular values that actually grow and the ones that don't grow. So in matrix factorization, this deep leads to larger gaps between singular values, so this will mean that we actually learn lower rank of the matrix. Any questions? So this result is similar to the one that Alberto showed before, but it's basically also saying that some of the standard ways of expressing the norm are not enough to capturing what is the regularization in the case of matrix factorization. Any question? Okay, if not, this two of the follow-up papers that are very related to this study are these two papers that actually keep using matrix factorization problems to study deep learning. So the first one is implicit regularization in deep learning might not be explained by norms. Basically, what they say is that, as we have seen by studying matrix factorization, we can see that the minimization of the norm can be the reason of regularization for some cases of neural networks. But we have also seen that for some cases, it looks like minimization of the norm is not what is happening. So this paper proved that exists natural matrix factorization problems on which the implicit regularization drive all norms to infinity, but still the result is regularized. And what is happening is that there is a minimization of the rank of the matrix. And in this case, they are going to explaining also for nonlinear neural networks. That the example that we have shown is only for linear neural networks. And in the follow-up paper, implicit regularization in tensor factorization, they actually apply this to tensors. So they basically do the same, but they try to take tensor completion via certain time of node linear neural networks. And basically, their study suggests that something very similar happening when the learning, the gradient descends to learning, but some kind of very greedy low tensor rank search. And this case is more interesting because actually this kind of tensor factorization can represent very up-to-date neural networks that are with nonlinearities and so on. So, any question?
Hi, Jezabel. I have a question about the previous slide where you talked about the singular values of the matrices. Does that apply to all matrices or just say certain kinds of matrices? For example, matrices with random Gaussian IID entries.
So they don't constrain the matrix in the paper. So I think it's applied to all matrices that have low rank. So if your growth through matrix have low rank, basically.
Okay, thank you.
Okay. So now we are gonna move to a different section of the talk, where we are going to discuss the study of implicit regularization in training conditions that are closer to real-world training by using a technique that is called backward analysis, backward error analysis. So sorry, we will see.
Can I ask about the last section first, actually? Sorry if I missed it, but I never understood the connection of the matrix factorization problem with like training a deep network, like.
Yeah, so basically, I don't know if so if you, when you want to do matrix complexion and you express your matrix as a multiplying matrix, basically what you have is kind of a linear neural network. This helps?
Sort of. I mean, like, so there's like two, there's the row and the column with the matrix, and I guess why is it that like I don't see any inputs in this equation? I guess I should just interpret one of these matrices as like a design matrix in the product from Wn to W1, or?
Sorry, you don't see that. I cannot hear you properly. Can you repeat the question?
Oh, yeah, sure. I don't see any inputs here, right? So I see like Yij, that's the target. But then this product of matrices, I was interpreting that as like the weight matrices. But then, there's no input that you're inputting into this sequence of matrix multiplications. So I'm wondering if I should just like interpret the first of these matrices as the data.
The first of these matrices, so the data will be the position of this EY, basically. So yeah, the final matrix. The row and the column is your data, and your label will be the value.
Yeah, so I see what like the label part. I just don't see the input part.
The input will be the position on the original matrix, basically.
So like as a 2D vector of real numbers?
Yeah. So yeah, basically you have this. You have a prediction of 1D for 1D to R.
Okay. Yeah, it's still not super clear, but thanks.
Okay, sorry. So I don't know where I was. I was here. So no, I was not here, no? Yes, I was here. Yeah, I was saying that we are gonna change topic now, and we are gonna try to discuss implicit regularization using, in the case of training conditions, much closer to real world training conditions. And for this, we are gonna use backward error analysis. And this is related to two papers of this year that appear in ICLR that are called Implicit Gradient Regularization, that basically study implicit regularization in full batch gradient descent. And a paper that actually follows up this paper that is on the origin of implicit regularization in stochastic gradient descent that will use the same technique to study stochastic gradient descent. So why this analysis is interesting? Well, because in all the previous studies, we use NTK, or we use gradient flow that are conditions that are very far away from real data training. And in real life training, we usually use batches, so we use SGD. And we know that large learning rates generalize better. And actually, we use random sampling on random shuffling in large data sets. And this is kind of not always considered in previous studies. In this work, especially in the second paper, they are going to study SGD. They are going to use small learning rates, but not infinitesimal ones. And they are going to use backward error analysis. This is not really studying real training conditions because they are using random shuffling, so the batches are fixed and the learning range is still small, but it's the closest to what is happening in training. That is the closest study to what is happening in training. So, okay, we will use a similarity between gradient flow and ODE to borrow an analysis tool from numerical integration. So we are going to use start by the most basic expression of gradient descent, where we take finite steps of our updates of the gradient of the loss. We know that if we take the limit of vanishing learning rate, gradient descent will become gradient flow. So gradient flow is used first order ordinary differential equation, ODE, and we know that there are tons of ODEs that we cannot solve. So we typically use some numerical method. The most standard numerical method for solving ODE, or the most basic one, is the Euler method, where we do a system of small updates to approximate the differential equation. So this approach of seeing our gradient descent as a differential equation will allow us to use backward error analysis to study the gradient descent. If we use Euler method to solve the ODE instead of a smooth curve, we have is a small step. Each one of them will diverge from the real path and will probably go to a different solution than the one that our original equation will have. So there will be a bias between the solution of the continuous ODE and the discrete iterations that we do using the Euler method. And we like to capture this bias and know what is happening. For this, we introduce a modified flow. It's a new fake equation that we can use to analyze this behavior. And basically it have two key properties. First, this is the Taylor expansion in power of the learning rate epsilon. And it have the correction step, the correction term F1 and F2 and so on. And in this expansion, the original vector field F is the original vector field. So in the limits of epsilon goes to 0, the modified flow is the flow. So these two values when the learning rates go to 0, these two things have to converge. So the goal of backward error analysis is to choose the correction term, F1, F2, and so on, that iterates such that the iterations obtained from discrete updates of the original flow with this small step size lie on the path taken by the continuous solution to the modified flow. So we want to select this F1 and F2 that follows this path. So basically what we need to do is calculating the correction terms. So how we do the calculation of the correction terms? I'm gonna show you how to arrive to the value of F1. So in our first step, what we will do is we will identify the path taken by the continuous modified flow by considering the combined influence of an infinite number of discrete steps in the limit of vanishing learning rate. So what we are doing is basically taking an n Euler steps on the modified flow with a step size alpha. Since this is this first line here, since now we know the relations in between omega t plus 1 and omega t, we substitute it here in this second line. And now what we are gonna do is do a Taylor expansion of alpha here. So using the formula for arithmetic series, we can count that the terms of alpha squared have, that we have this number of terms on alpha squared, and we are gonna ignore higher orders of alpha. This is only okay if this n3 by alpha is small and is one of the limitations of the paper. So then what we are gonna do is like to ensure that Wt plus n coincides with the solution, Wt plus epsilon. We are gonna take an infinite number of steps, and we are also are gonna take the limit where alpha goes to, we are gonna take express alpha as the learning rate divided by the number of steps. So this is what we get here, and now we have f tilde here, and we can substitute it by our value of modified flow. Okay, so these first two terms of the equation are going to be exactly one Euler step, and therefore, in order to ensure the continuous modified flow coincides with the discrete update, all these terms have to be 0. And this allows us to get the value of F1. Okay. So we here have the expression of the original differential equation, and we can substitute in the value of F1, and we get this expression for the first correction term. Okay, so why is this interesting? So we originally have a const function C and our differential equation with this form. And we know that if the gradient descent stays close to the ODE, we should have this equality. We have our modified flow with this form, and we have the F1 value for the modified flow. So if we do this, we will arrive to a new modified ODE where that have exactly the same form that the original one, but where the cost is not the cost that we have before, but the original cost or the original loss function plus a correction term. So this correction term will be our regularization term, and as we can see, it penalizes the large norm of the gradients of the cost. So, and it will be proportional to our learning rate. So basically what we are saying is that running gradient descent will be equivalent to running gradient flow with a rectification term that is penalizing large norm of the gradients. So they basically illustrate this result with a very simple two-linear model where A and B are the parameters of the model, and they compare implicit gradient regularization and explicit gradient regularization. The arrows are basically the gradient flow at each step. This is the global minima. That is basically a hyperbola for the solution. The gradient descent trajectories start from two different initializations. So this one is out of the graph. But basically, we can see that for the small learning rates, the gradient descent trajectory follows the exact gradient flow closely. Or not exact, but very closely. So this basically reinforces the results that we have seen before. So this is for gradient descent, but in most of real-world experiments, we train using batches. So this result, or arriving to a similar result of doing backward error analysis for SGD, or the demonstration is a bit more complicated. So because the trajectory is stochastic, so therefore you don't have a single direct trajectory to optimize, but instead you have a distributions of different trajectories which you will follow if you random shuffle your data. So starting from this initial point, we now have these multiple trajectories. Each one corresponds to a different way of shuffling the data. In the paper, they use random shuffling, and it's going to be key for the proof, and not random sampling. So the difference is that in random shuffling, you have the data already assigned to your batch, and you shuffle the batch, not that you sample all the data in different batch each time. So there is a fixed allocation of data points to mini-batch, and the randomness comes from the order in which the mini-batch are considered. So in this plot, the orange trajectory illustrates two potential paths. The path will end in different random locations. So each of these arrows will be a possible other ending of different path. The orange diamond shows the mean of the distribution of random trajectories. So similarity to the previous case, the goal is to reverse engineering the ODE so that the continuous blue path lies close to this mean location. The demonstration for HGD is a bit more complicated than the one that we just have made, but they are going to show that these agains correspond to have a modified ODE where your cost function have now not a single value not a single value of the gradient of the cost or the norm of the gradient of the cost, but there will be the sum and the mean of all the possible batches. So it's important to know that while the loss function of gradient descent have the same minima of the original loss function, this is no longer true for SED. So minima of the original loss, where the variance of the gradients is high, is no longer a solution of the minimum of the SGD. And the implication is not only SGD follows different trajectory that full batch, it might also converge to completely different solutions. So basically, they have found a regularization term for SED that should produce best test accuracy that if this regularization term doesn't exist. For the analysis, they train the same model with two different loss functions. So this was or modify loss function from the gradient flow. They are gonna basically train the model with C mode for different values of lambda. So when lambda is 0, you will have that your loss is your original loss, and when lambda is different to 0, you will introduce this explicit regularization with the form of the implicit regularization that we find before. So in the figure A, we have the test accuracy against the training epochs, so the training curve, basically, where the blue line represents the original loss, and the orange line is obtained by use a modified loss that include this explicit regularization with the value of lambda of 2 -6. So at the end of training, we can see that this is trained in gradient flow, basically with a value of epsilon that is the learning rate very small. And at the end of training, we can see is that this explicit term that corresponds to the implicit term that we will have in training, it makes that the test accuracy is higher, so you have a better result. In the second figure, they have a second experiment where they try to check not only that the explicit regularization term improves the training, but also that the optimal value of the explicit coefficient lambda is the same that the optimal learning rate for the original learning rate epsilon. So in the x-axis, we have the learning rate, that is epsilon, but also the regularization scale that will be lambda. For the blue curve, they train with original cost function and moving to the right, they are changing the learning rate. And they find an optimal value of the learning rate here, that is epsilon, the optimal value of epsilon. For the orange curve, they fix a small value of learning rate of 2 to the -9. And as we move to the right, where they are changing, is the coefficient of the regularization, lambda. So they also find the maximum value for the regularization, and these two curves have a similar path, and they find that these two maximum values are close. So they both have a similar peak, and the value and the value of lambda and epsilons are pretty close. That is what we will expect from our implicit regularization expression.
Sorry, what's the data sets here?
Oh, yeah, I forgot. So they were training wide ResNet without batch normalization in CIFAR10.
Okay, thanks.
Yeah. So basically, this is my this is my last slide. We have basically seen that you can show that gradient descent have some implicit regularization term when you compare it with gradient flow. Alberto, do you want to go for the discussion?
Yeah, so we just have a list here of work that basically have been developed, and some applications as well. Following this the development of these theories. Yeah, so for example, the first one is about doing simulated nonlinearing by increasing the batch size instead of the learning rate. So that was also quite a popular approach. The second one is an interesting recent paper that shows that if you inject noise into gradient descent, it's not the same as the mini-batch noise. So mini-batch noise seems to be special. It actually works better than just if you just inject noise in gradient descent. And some people do it, for example, for sampling posterior of the distribution of the posterior of the parameters, right? The third one is about actually using matrix factorization into neural networks. So as David was asking, the example shown by Jezabel is not exactly cannot exactly be mapped into deep neural networks, but so there have been people applying this matrix factorization into deep neural networks. Basically, the idea is that you expand synchron matrices into matrix products during training, so you get low rank solution for these matrices, and then during inference you can just run a forward pass through a single matrix. So it's also some sort of regularization that is being used. Then also people have shown that if you do ADAM or other adaptive optimizers instead of gradient descent, they also do some implicitly regularize. Yeah, so there are also interesting work, label noise, the existence, some special cases where SGD actually finds bad minima. So yeah, overall, I think this is exciting topic. There are a lot of interesting papers published, very all the time. So yeah, if you're interested, we have we just list all these papers in the references at the end of the presentation, so you can look at them by yourself. Yeah, that's all. Thanks.
Alberto and Jezabel. I think we're at our half-past time now. So if you have somewhere to go, then feel free to go. If you have any questions, and if Alberto and Jezabel can stick around for another 5 minutes, then please do come ask them, or ask them over Zoom. Cool, thank you. Okay, first question.
Hi, thanks for the talk. And I just sort of thinking about the way you structured it, dividing it into 3 sections. It seemed to me like the first section about preferring flat minima or wide minima over narrow minima, and the third section about implicit regularization of essentially penalizing the gradient norm seems sort of like the same thing. I don't know. What are your thoughts on that?
So you said the first one and the third one?
Yeah, like they both essentially seem like finding like not narrow or finding wide minima, but in different.
Yeah, so it's not exactly the same because so the third, okay, so the third section is about so the first part of the third section, I hope you don't get confused now, is about the gradient descent, so full batch, right? And so even so, if you do full batch gradient descent, then there's no mini batch noise. Still, when you compare it to gradient flow, you're gonna find something different, and that theory, it basically tells you what is the difference. And the difference is this regularizer that penalizes big gradients, which is different from penalizing big curvature, right?
Okay. I forgot that the difference is stochastic versus full batch. Makes sense. Thanks.
Yeah.